So I would say we get started. I would like to welcome everyone to our Architects Focus presentation, Closing the Gap in New York City, presented by Handel Architects and Stephen Winter Associates. Both offices have quite an extensive experience with large passive house design, and I'm very excited to have both offices today present Sendero Verde under construction in an evolving industry. I would like to thank Handel Architects for being a supporter and a sponsor of New Passive House throughout the years. We really appreciate your support. It's my pleasure to welcome Buck Moorhead, who is a New Passive House board member and fellow architect, and will introduce today's presenters. So Buck, please take it away.
Hi, everybody. Thank you for joining. We're very excited to hear this presentation. Just a couple quick words about Ryan, Lewis, and Dylan here. Ryan Lobello is a senior associate with Handel Associates. He's the project architect for Sendero Verde, and is also the project architect at Cornell Tech as well. He's known as the guy. This trio has been around the block, so to speak, and he's known as the guy with the passive house, with the shtick about passive house, so to speak. Louis Koehl is an associate with Handel Architects. He is administrating the construction for Sendero Verde. He's also in the process of designing University of Toronto at Scarborough, a dormitory project there, which is a facade, I guess predominantly a facade project. He's known as the badass of this trio. Maybe we'll learn how that came up. I'm not quite sure. And Dylan Martello is a senior building systems consultant with Stephen Winter Associates. He's the passive house consultant, and he's known as the sage member of the trio. So welcome to all three of you. Thank you for joining us.
Great. Well, thanks, Andreas. Thanks, Buck. And thank you. I see a bunch of friends out here. Thanks to NYPH for hosting us digitally again. Last summer, Louis and I presented an overview of 4 multifamily and mixed use passive house projects, large scale projects. But tonight we're going to do something a little different. We're going to have like a deeper dive specifically into Sendero Verde. Think of it more as like a construction update. We're also going to broaden out a bit at the end to discuss some bigger picture topics about the ever evolving New York City construction landscape. Go to next slide for a second. So we're going to speak about many topics today, but wanted to get your brain starting to think about some of these items here. And at the end, we're hoping to have some conversation with you to discuss, like how do we determine what buffer to hold at certain passive house criteria? What type of materials, that maybe we started using in passive house projects, but now we're able to use in our typical non-passive house projects as well. Some surprises, adaptations, other pinch points, and how we can use like testing protocols throughout the CA process as teaching tools with the team and with the construction and the subs as well. So just start to think about this. We touch on a bunch of these things throughout the presentation today, and then we'll hopefully have a discussion afterwards. Let's go to the next one. So we presented this project a lot in the past few years, but let's just do a quick refresher. Sendero Verde is located in East Harlem. It's a 100% affordable housing, multi-building project with Jonathan Rose Companies, L&M Development, the Acacia Network, and New York City's Housing Preservation Development Department. We have a great design team. In addition to Handel Architects, we have Stephen Winters as our passive house and sustainability consultant. This is an Enterprise Green Communities project. Cosentini is our MEP engineers, D. Simone for structural, and then Vidaris for exterior wall. The construction manager on the job is also a fantastic team from L&M Builders Group. So Sendero Verde is organized with the tower as building A and the low rise as buildings B North and B South. Now building A right now is going through bank closing and is scheduled to start construction this fall. Building B is the project that's under construction, and that's going to be our focus today. Taking just a big picture look at this, Sendero is a 100% affordable housing project. And one of the client partners, Jonathan Rose, he believes that affordable housing is a connector for the community, and we believe that too. He describes his approach here. You can see the little diagram at the bottom. He describes it as a community of opportunity. And it's about weaving together local culture, arts, healthcare, recreation, recreation space, environmental responsibility, and all these other planks, all these other goals. And sustainability is like one weave in this kind of larger picture. And all these components connect neighborhoods together, and they can become a catalyst for social and urban change. Looking at the diagram there, you can see that the upper floors of Sendero are housing, while the podium has this robust community facility program. In B North, that project has a K-5 charter school by Harlem Children's Zone. In B South, there's Union Settlement, which is, I don't know how much you guys know about settlement houses. These are like uniquely New York institutions, and Union Settlement is like one of the largest and oldest New York City settlement houses, and it's been based in East Harlem for over 125 years. In Building A, we're going to have an art gallery and an event space by Acacia. There's also 4 relocated community gardens on the site, as well as a large central courtyard that's open to all residents and the public. One of the important things for us here, at Handel Architects, and I think important to the NYPH community, is like this project is really showing how passive house is compatible with like aggressive affordability. And through our partnership with New York City's HPD, we've been able to prove that passive house works at an affordable housing price point. Sendero Verde is funded through the ELA program. I'm not going to get too much into this, but it stands for extremely low and low income affordability. And basically 25% of the units are mandatory inclusionary housing. All of the AMIs are less than 100%. And we have some earmarks that 10% of our units are dedicated to formerly homeless households. And so like this population, it requires significant social services programming. It's really quite cool. There's like in the base, in the podium of B North, we have like these group therapy rooms. There's like kitchen and home ec classes. There's even, doctors and dentist hours throughout the week. And it's an effort to try and help smooth transitions and bring people back into their community. And then just real briefly, here are the sections through both Building A and both Building B. You can see that the affordable housing in the upper portion is that's a certified area, but the entire building is enclosed by that airtight envelope. And the reason we pulled the community facility spaces out of the certifying boundary, but they still have an airtight facade. And this is because the tenants they're nonprofits. They may not have the budget to meet passive house initially, but we allow them that choice. So in the future, they can opt in. And these community facilities, they don't have the passive house requirements for insulation and thermal comfort criteria. And the main distinction is that the windows are air sealed to passive house standard, but they typically are double paned. And for the passive house boundary, and like the lobby and the residential spaces, it's all triple paned. So I think that's a good overview. Let's go to the next slide, and Dylan, take over.
Yeah, thanks, Ryan. So, one of the things, we're going to get into some technical stuff here. And one of the things I want to mention is that the passive house concept applies really, really well to larger scale, especially multifamily buildings. Now, think of it as you compare a house to an apartment. A house has essentially 6 sides of its building surrounding of enclosure area surrounding the usable square footage. When you have a multifamily building, if you look at sort of the typical apartment that's not necessarily a corner at the top of the building, it really only has one side of exterior surface area. So what happens is you get this benefit with large scale buildings where you have a lot of interior air volume and a lot of usable square footage, but relatively speaking, not as much square footage of surface area that you will lose heat to. So what happens as a result of this is you actually end up needing less insulation levels to meet the passive house criteria. So we wanted to compare, because we're going to show results from B South and B North and get into the exterior wall assemblies of each and show you the difference between B South and B North. And you can see here that B North is approximately almost 4 times the building's air volume as B South. And that will really play into the levels of insulation that were required on this project. One great update is that we can share is both buildings are pre-certified. So B South and B North through the Passive House Institute. We're very excited about that. It's a very good milestone. And it's something that I feel is critical on every project to ensure that you have a grounding going into construction, that we cannot deviate from this level of performance because we have been pre-certified to this level. And it really gives you something to stand on when you're working with contractors and the team throughout construction. So if we look at Sendero Verde B South, what we're showing here is the energy modeling results, the energy modeling as predicted by the PHPP, both at the feasibility stage and where we're at currently. And one of the things I really want to speak to here is why we build in a buffer. And we do this on many different levels. So if you see here, our heating demand for B South is in feasibility stage at 4.15, and the criteria is 4.75. We always like to target somewhere around 4. It can be a little bit higher if we need to. It sometimes is a little bit more difficult depending on the project, but it's really good to target right around 4 and really not creep much higher than that when you're in a feasibility stage. The reason being is as you go through construction and as you go through even construction documents and the design process, there's going to be little changes that sort of tug and pull on the model. And usually those changes end up increasing your heating demand slightly. So you want to give yourself that buffer. And you can see currently we're at 4.48. So that buffer has come in handy. The cooling demand on this project is an interesting one. And it relates to largely the occupancy assumption of this project. And when we started in feasibility stage, we assumed the standard PHI assumption for occupancy, which there's a formula that we use. When we were about midway through the design, we had PHI do a preliminary review of our documentation. And one of the things that they asked us to do in this project was to use the predicted actual occupancy of the project, not PHI's assumption. And that came in about 30% higher. The actual was about 30% higher than what PHI's formula predicted. So we ran with that assumption. And as a result, our cooling demand, because we have more internal heat gains from those people, went from 3.8 to 4.41. Now, one thing to keep in mind here is that the threshold also went from 5.71 up to 6.66. So the PHPP does give you some allowance depending on the amount of internal heat gains in the space. That's purely a function of things you can't control, like building density and occupancy. We also give ourselves buffer and air tightness. Now, this one is critical. The reason being is that the last thing you want to happen is, let's say you have an energy model and you're feeling very confident. You're like, we're going to get 0.3 air changes per hour when we test this blower, when we do the blower door test for this building. And you use that to meet your energy demand thresholds. The last thing you want to happen is the project actually passes with, let's say, a 0.55 air change per hour at the final blower door test. And if you run that in your model and you were assuming a much lower value at that point, then you run the risk of not actually meeting your heating or cooling demand thresholds. That's a really problematic thing. So what we do is when we do any model, we're modeling the lowest, the absolute minimum level of pass-fail air tightness, which for this project is 0.6 air changes per hour because it's new construction through the PHI standard. Now, the last thing here is on primary energy. So when we started this project, our threshold was 38. Now, about 2 years ago, PHI released an update to the program that calculates a project-specific PE or PER threshold for any multifamily building, especially buildings that have high density. And there's 2 factors here that is resulting in the PE increase from feasibility to current. One is that occupancy, the occupancy increase, and that is what is increasing our actual PE demand. And then the PER threshold, or the PE threshold adjustment calculator, is why we went from 38 as a criteria up to 58.5 for this building. So that threshold is now sort of flexible depending on the occupancy of the building and the sort of density. So that's something that's very clear, or something that we've experienced as a result of going through this process on B South. Now we look at B North, as coming back to my previous point, if you look specifically at the heating demand threshold, which is really going to dictate how much insulation you need in your walls, that is much more comfortably below our threshold, even in feasibility, and now currently we're in, almost half of what the threshold is. So we're comfortably below that. And as Lewis will get into in a few minutes, we'll be able to see the difference in levels of insulation that were required for this project. And again, this is all related to the building's air volume. And the same thing holds true across the board from the cooling demand perspective with regards to occupancy, our air tightness assumption being conservative as possible there, and on the primary energy thresholds as well.
All right, thanks, Dylan. So I'm going to talk a little bit about the facades of the building here on B North, and also I'm going to touch on building A as well, just more for reference. So on the left side here, we have the design detail for the typical wall in building A. Building A is a brick facade all the way up the tower. We designed this one first, and so that was kind of driving the initial part of the project here. So it's a stud backup wall with mineral wool insulation. We have continuous mineral wool insulation in the brick cavity here. And then we have our airtight layer, which is our waterproofing behind the brick. And then we have a vapor control layer to keep moisture out of the insulation on the warm side of the air barrier. So that's on building A, where we had a brick facade. You can see on building B, where we primarily have an EIFS facade, there's a lot less insulation. So over here, we were looking at 9 inches of insulation, 6 inch in the cavity, 3 inch continuous. Here we're looking at 4 to 6 inches of insulation. The 4 inches is on B North and the 6 inches is on B South. There's some minor areas where that deviates, but that's generally the case here. And that's indicative of that heating demand that Dylan was getting into there, where we had a lot more comfort on B North than on B South, just because of the volume of the building. But EIFS is it's a challenging material to work with aesthetically, but it's a great material from a thermal standpoint. There's no thermal bridging. You can install it after the windows, so you can overlap the window frame and get really good install values on your windows. So we end up getting, an R24 effective here with this wall typically. We have UPVC windows in here. We do have some brick facade on building B North. And that area is a similar detail to what we're seeing here. But for the most part, we're dealing with EIFS in the passive house certified boundary. So this is a good construction photo, kind of showing the layers of the EIFS as it's being constructed. You see the Dens glass, and then the blue is the air barrier and the waterproofing. The white is the EPS insulation. The gray is the mesh and base coat. And then you have your finish coats going on. This is not quite the finish. There's one more on there that'll give it a little bit more vibrancy. So you can really see that there's no thermal bridging going on in here. It's just continuous insulation all the way up. We do have some deflection joints at the slabs and some drainage joints. The deflection joints are just in the finish. The drainage joints do go all the way through. So every 3 floors or so, we have a linear thermal bridge. But otherwise, it's a pretty continuous facade. The insulation was something that we really were focused on with the project. We wanted to try to minimize the amount of carbon, the embodied carbon in the project, which, for that reason, we didn't go with XPS, just because you can see how big an impact XPS has, even though it is a higher R value. We opted for a lower R value in the exterior wall insulation, just to get that carbon down. We thought it was a worthwhile trade-off. We end up with maybe an inch more insulation, but a significant improvement in the overall carbon. We wanted to go with mineral wool, but at the time there was not a mineral wool system on the market. Thankfully there is now. So on our next project, we'll be looking to employ that the next time we're using EIFS. There are some thermal bridges with EIFS at the bottom of the wall. Basically anywhere where it needs to drain, there's a thermal bridge. So at the bottom of the wall, we had a situation where we needed to get flashing up behind the drainage plane. Typically, you would turn that flashing up the wall, and that would be a pretty significant thermal bridge. What we did was we cut the flashing short. So you have the stainless steel, it comes, it stops before it gets to the wall, and then we're lapping over that flashing with a membrane flashing that's coming down off of the air barrier. So that limits the thermal impact of that detail. Similarly, at the window heads, we Drive It wanted us to have a piece of flashing here. We revised this detail to get rid of that flashing by having this J-track embedded above the window within the EIFS system. And you can't tell in this image, but this track is actually sloped. So any water that comes down the wall, it hits that track and then it runs off the side of the window. And that allows us to have no flashing above the window head, which is nice aesthetically and then also from a thermal standpoint. Other thermal bridges we're dealing with, we have some significant structural thermal bridges at things like canopies. We have a big steel canopy that we, at all of our entrances, and we have a structural thermal break there, a steel to steel thermal break. We had to spend a lot of time coordinating this, getting this thing sized and oriented correctly to get through our storefront there. We have structural thermal breaks below curbs for larger equipment. This is for our generator. And at places with a little less engineering required, we're using the general plastics. So like dunnage, this is our PV dunnage, our post for our PV system, ladders, OSHA rails, we're using the general plastic stuff. It's a lot easier to work with on site. Then there's AAC block. We're using this significantly throughout the project. And really, this is a product that we're using on non-passive house projects now as well. It's a very versatile product. This is it at the parapets here, 2 courses of AAC. That's the lighter colored block, and then the CMU above. And then this is already wrapped in waterproofing, but this down here is AAC sitting beneath the brick. So in the locations down at the ground floor and the second floor, where we have brick coming down to our courtyard or our grade, we can set that up on an AAC shelf. That parapet detail is really one that we're looking to use everywhere, both passive house and non-passive house, just because it really simplifies what is a generally complicated detail. You can see the therm model here with 2 courses of AAC. It really just eliminates any thermal bridging from the parapet into the space. And this is without wrapping this thing. Typically, we'd be wrapping the parapet in insulation, trying to tie it into the roof insulation. That makes the waterproofing more difficult. It's a kind of expensive detail, a lot of opportunity for error. So this allows us to do this very simply. The AAC is the same module as CMU. So you're able to get a CMU block above, which we like because we like to mount the railings into the CMU, not into the AAC. It's got a little bit higher structural capacity. So this allows us to get our parapet mounted railings mounted directly to the CMU. And then, you have a completely thermally broken railing system, and all, very cost effective through that AAC system. Another point of significant thermal bridging was the shelf angles. So there is limited brick scope in the passive house envelope, but there is some. So this detail was largely developed for building A, but we pulled it onto building B where applicable. We knew that this detail was going to be tricky with our window heads, but we wanted to build or design a detail that was, cost effective and something that the masons could really get in there and do from day one, not reinventing the wheel here. So we looked at a series of different systems, but the thing that seemed to work the best was using a thermal shim from Armatherm. And you can see we tweaked this therm model a bunch of different ways, trying to get the shim depth just right, so that we could get that thermal comfort criteria right at the face of the window. And then even though we do have some heat loss at this window head, we offset that with the U value of the window, the frame, the glass, the other install conditions. And here's a photo of that shelf angle condition. You can see the thermal shim there. We had determined that it needed to be 3/4 inch deep for our thermal performance. So whenever it's deeper than that, they can just use typical shims. And then in between the shims, we're filling the cavity with mineral wool insulation. On building A, we're going to need to use spray foam to get a little bit higher value, but our value. But here we were able to work with mineral wool in the model. Another kind of unique detail that we were dealing with here at the brick. And you see these are all brick details because the eaves details are really straightforward. It's with the windows for the eaves, they're installed in the wall, the window is aligned to the backup wall, and then the eaves just comes right across the edge of the frame, giving us a good thermal condition. That's possible because the eaves is able to be installed after the windows are installed. With the brick, we wanted to be able to install the brick first. So we developed this detail here to minimize the thermal bridging at the jambs while also allowing the brick to be installed first. So the brick is installed against this blocking. So we have a single piece of blocking here that acts as a cavity closure. It allows for the, excuse me, it allows for the insulation to get as close to the window frame as possible. We have a little additional spray foam insulation in there to fill that gap. And then the brick is sealed to the window, and the window can be brought into place from the inside and sealed into place there. And this is a photo of the blocking wrapped in the air barrier before the window's installed, and this is from the outside after the window's installed.
Yeah, so one of the things we wanted to highlight here, because this project is so unique in that there are passive house elements and passive house areas of the facade, and then there's sort of non-passive house areas as well. We feel that this is a really good sort of potential case study for essentially looking at how we can impact normal construction practices on every project, not just passive house projects. So what I wanted to highlight here was how we actually worked with a sort of non-passive house rated window system. It's a metal window system, and it uses receptors. So on the right is actually what you're looking at there is actually the receptor that goes under the window. And I'll be honest, when we started this project and talked about receptors, I was a little nervous. And there's certainly some air sealing measures that we've discovered, one of which is where the receptors on this system meet at corners. We found that if those corners are caulked and set in sealant before they're sort of fastened to the rough openings, that provides an additional level of air sealing that helps us get to a passive house level of air tightness on a window that's not actually meant to be performing to that extremely low passive house level of air tightness. Another element here, which is shown on the left, is the sort of flashing at the base that causes a potential for air leakage. And thing I'll mention here is I'm not speaking in terms of theory here. We actually tested this window, and we determined that when we did our test at the sort of first pass, they were a bit over our threshold for air tightness. And they came up with these additional measures to get to a passing threshold from an air tightness perspective, roughly around 0.1 CFM per square foot of facade or window area. So you can see setting that sill flashing in sealant, that sill pan in sealant provides an additional level of air sealing that we found to be critical on this specific system. We've also determined that some corner seams as well. We worked with the contractor to see if that would help. And I think that provided some benefit, but the interior stuff didn't work as much as some of the exterior measures and the caulking of the receptor and the flashing were. But it was another measure that we took that had some impact. The other aspect here is that the photo on the right, what this is showing here is this is the top corner of a window where the operable sash essentially will close into. And in green here is where the normal gasket is located at the jamb for that. And that's providing our sort of airtight connection to the window. Now in red, that circled area in red, this window manufacturer couldn't actually, the way the system was designed, they needed to leave about a 3-inch gap between the gasket termination and the top of the window, which is that red area, for pressure relief. And this is one of those aspects of, again, this window wasn't really designed to be a passive house level of air tightness. So what we had to do was pay extra attention to those other areas, like at the sill and at the receptors, to make up for that, because they actually couldn't close that gap because they need it for the performance of their system and pressure relief. With passive house windows, we generally see that the weep holes are typically sufficient for pressure relief. So when we're talking about air tightness, one of the measures that are really truly a valuable test that we do is we do what's called a guarded blower door test, where you essentially pressurize the floor above and the floor below the actual floor that you want to test and get air leakage on. So if we want to look at the air leakage on floor 4, we're going to actually pressurize floors 5 and 3 as well as floor 4. And what that does is it isolates any air leakage in theory to the floors above and below. So what happens is you're only really going to, in theory, be getting the air leakage through the exterior facade on that test floor, in this case, floor 4. But what this also requires is for us to build some temporary walls. And this is where the test can get a little dicey. And in this case for Sendero B South, which is where we did this test, is we had to create temporary walls and temporary seals at the stairwell shaft, the elevator shafts, and also for the temporary hoist. This photo here on the left shows some of these temporary walls. So this is, I believe, at the elevator shafts, and we're, essentially requiring the contractor to build out a shaft or a sort of drywall or sheetrock sort of assembly with all of the tapes and seams sealed, or all of the seams sealed. And this is really to allow us to, again, just focus on the air leakage and look at getting the air leakage through the exterior shell, which is what we care about. But one of the things it's really helpful for is looking at a large array of windows performance. So, you know, we might have 30 to 40 windows on a floor. And when we're running this test, we can go around to every window and check, and we'll feel around. We'll bring theatrical fog, we'll bring smoke puffers, smoke pens. In this case, what we did is there was a few windows on B South that weren't adjusted properly at the time of the test, and this is one of them. So what we did is we taped it off at first to see what our air leakage number was at sort of a base level. And then if you go to the next slide, then what we did is we took the tape off and we looked at the air leakage, the CFM of air leakage, which was in this case 1300, shown here on the right, at 50 pascals of pressure. And we had the window contractor there with us, and we were adjusting the window to set, essentially set it in the rough opening more properly, so it seals and that window can actually crank in and really seal shut. And after making those adjustments, we were able to cut out 150 CFM, which is a lot for one window. You know, we're talking the blower door, the whole building blower door air leakage number might be on the order of, you know, 5,000 or 6,000, 10,000, depending on the size. But when you can cut out 150 CFM in one window just by adjusting it properly, this is where we feel there's a true value from doing this test. Now on B North, it was a little bit trickier. We couldn't do this because of the size of the building. The way the EFIS wall had to be constructed is they had to go by what's commonly referred to as EFIS drops, or drops down the facade. And this had to be done by orientation. So the problem here is that if we waited for the entire facade to be finished, or in order for us to do the test, we have to have the facade be completed because we want to make sure that the air barrier system is installed. And if we waited for that to happen, all of the facade would have been installed at that point. So the guarded test didn't make any sense because there was no logical time for us to actually do it. So what we did instead on this project, we took an isolated portion of the facade, about a 40-foot span on the north terrace on B North, which is highlighted there in blue. You can go to the next slide. And we created our own chamber. So this is something we've done a couple times on a couple of projects now. And we've found this to be a very valuable test, and it's sort of accomplishing the same thing as the guarded test, just on a much smaller area. But the photo there on the left is showing some of our prep work, and we have to sort of create these custom like foam blocks to kind of keep our plastic shroud. When we depressurize that area, we need to make sure that there's enough of an air bubble allowing air to get from everywhere on the facade. We want to make sure it doesn't just suck tight to the actual air barrier, because then it wouldn't be a valid test. The photo on the right here is showing the test in pressurization. So it's pulling that air through the bubble, and it's essentially pushing air into the bubble and having it bulge out. And you know, one of the things we always like to do when we do these tests is have fun. So this photo here on the left is showing us just kind of messing around a bit, and it helps to keep things a little bit lighthearted when you're doing such intense work sometimes. But at the end of the day, too, we're here to do our job. And one of the things that we were proud of on this project in working with L&M builders was, you know, this actually yielded a passing result the first time we did this test. And so the number there, 24.8, is the CFM through that entire 40-foot by about 10 or 11 feet section of facade of CFM at 50 pascals of pressure. And the threshold was about in the low 30s. So we were comfortably below that threshold, and we were you know, proud of the work that L&M builders had done on that. And if you go to the next slide, these are some photos of those actual windows. So this is the level of air sealing and caulking and completeness that we need to be replicated throughout the entire project. So we were there with the contractors and the builders, showing them, you know, this worked, this is the level of quality we need, and it almost serves as like a mock-up in a way for the future windows that are sealed.
Yeah, so this is not Sendero. So those of you may remember this. This is the Cornell Tech's plan, but just kind of like showing how you know, we learn from previous projects and kind of like knowledge sharing and what happens in the passive house industries. We all kind of like see how other people are doing it, and we're always evolving. And so like what Dylan was just talking about, when you end up having such a robust envelope, then obviously there are lighter loads on the mechanical system. And this allows us to use primarily VRF systems, which pairs nicely with electrification initiatives and reducing our reliance on fossil fuels. And Sendero Tower, we followed a very similar strategy to this at Cornell Tech. It's a split VRF system with a condenser porch outside the thermal envelope that requires thermal breaks. And then we have condenser loops that feed evaporators in each unit. And in Cornell Tech, it was split between north and south. But then when we got to the Sendero Tower, we had those internal refrigerant loops and split it into 3 zones just because of site orientation. Let's go to the next slide. So for Sendero B, we didn't have a condenser porch. We located the condensers on the roof with vertical refrigerant paths. This is kind of a more standard arrangement. It obviously takes up less floor area. But because we also are using the rooftops for amenity space, predominantly facing south, you know, for orientation and sunlight, on the south side, we located all the condensers up at like the main bulkhead roof so that we could clear the space for programming. And then on the image on the right, that's kind of a diagram of like a north side distribution where we were able to put the condensers lower on the setback roof, which is a little bit more efficient. It's shorter distribution strategy.
Yeah, so for this Sendero Verde project as a whole, we set out during the sort of schematic design and planning phase to look at what sort of HVAC systems we actually had, and specifically the heating and cooling systems that we had available to use for this project, and what our options were. One of the things we looked at was the potential to use a sort of PTAC style unit, or a VTAC is what it was called. It's essentially a vertical PTAC. And we tested one of these units, I think it was back in 2017, and it was like, I would say at least 10 times more air leaky than we needed it to be for passive house. So we sort of ruled that one out off the bat. You know, we understand that it provides an enormous pro in that it is very familiar with trades, and it's something that is certainly not you know, as expensive as some of the other systems out there, but we just didn't have a path for it. The other option that we looked at the start of the project was using a water source based system, or a hydronic system that used water source heat pumps and a centralized heating plant and a centralized cooling plant. Now, this one is interesting because today we actually have a path in passive house to do that. And one of the reasons why is we get a little bit of a primary energy allowance that is useful for the pumping energy associated with the system as a result of the multifamily threshold adjustment. So that's actually opened the door up for this type of system. When we started this project, we actually ran an analysis on using the system and with the actual pumping energy we expected, and it pushed us over the PE threshold. So we couldn't use it at that time. So ultimately, you know, as Ryan mentioned, we went with the VRF system for this project. So one update to this is that we actually have now tested 2 PTAC style units that are available in the US market today. And this is photos from the testing of that unit. And we determined that there actually is a path for this system. There are not at it's sort of like factory state. It's not to the level of passive house, but we came up as a result of this testing and working with the manufacturers, we came up with specific measures that the manufacturer can take to get to a passive house level. Because when we tested it, it wasn't that much over our threshold as much. It wasn't 10 times leakier. It was maybe 1.5 or 2 times. And we knew that if they took these extra measures, they could get there. These are some of those measures. So, you know, really what we're looking at here is the table at the top is showing our target for this test, which was 0.67375 CFM50. It's a lot of decimal points, but we'll just say 0.7. And when we did the initial test and depressurization, the leakage was at 1.7. So it was, you know, about 2 or 3 times over, but again, within striking distance. And when we made these improvements, which are shown here at the bottom, these 1 through 8 air tightness measures, we were able to get it very close to that threshold and essentially, you know, get it to a level that we felt comfortable with. So what these measures are, it's the actual seams at the sheet metal sort of box around it that need to be sealed. In this case, in the test, we actually sealed it with metal tape to simulate that. Weather stripping at the perimeter of the sleeve and make sure that the PTAC is actually sealed tightly when it's installed. So ensuring that it's installed right. You don't need a knockout for fresh air with these units. We're providing fresh air through our ERV system and the ventilation air, which is a centralized system in this case. So making sure that that's not installed in this specific context, if you have ventilation from another system, will help, again, reduce air leakage. P-traps filled with water, refrigerant line and electrical line penetrations coming through the casing is also an important thing to air seal as well. And then dealing with straps as well is another aspect that we determined. So here are some photos of those specific measures. So on the left, you can see that metal tape sealing of the seam there at the casement. We have the electrical line penetrations through getting some extra caulk there at the penetrations in the middle. And on the right, the refrigerant line is also being sealed. One thing that still needs to be dealt with these units though is while they are insulated, they are not going to be insulated very well to the level of performance that the exterior wall is at. So if your wall is at an R25, these units may be at best like an R5 when you factor in the thermal bridging of the actual unit. So you really need to, if you're contemplating using these, you need to sort of bake that into your analysis at the start of the project so you can design your insulation levels on the rest of the building to accommodate for that. One of the things that this is not Sendero Verde, but one of the things that I think we're all probably anxious for is some heat pump water heater options, specifically for domestic hot water. There are 2 pilot projects going on right now in New York City that we actually are part of and teaming up with NYSERDA on, and they're shown here on the left and right, where we're using ganged sand-in heat pump water heaters, which are a CO2 refrigerant-based water heater, which offers a number of benefits. One being the global warming potential of CO2 is one, it's CO2 itself. And the other benefit is that CO2 actually makes for a great refrigerant for hot water when you're looking at the temperatures that we need hot water to be. So this is an ongoing study. We hope to have more updates in the next few months, but we actually are in the phase now of collecting actual data. These have been in operation for about a month or 2, and we're kind of going through the commissioning phase right now. So we hope to be able to apply it to projects like Sendero Verde in the future as newer projects are developed.
Yeah, so let me jump in here real quick. On the HVAC installation, most of our studio apartments are using wall-mounted VRF consoles. All the other units are using these VRF closets here on the left. It's an upright EVAP that ducts heating and cooling to each space in the unit. And then these closets, it's a louvered door, and then they're accessed only by building operations. And then on the right is a cool product that greatly simplifies construction, like the L&M Builders Group love this. And you know, these VRF refrigerant route collection hubs. I actually forget their actual technical name, but that's what they are. They're this hub. It's just, you have these condenser farms up on the roof, and all the refrigerant, you would have multiple penetrations in the slab. Although what's nice about this, it all goes to one location, and then down into the building, it's only one roof penetration rather than multiple. And it's only one thermal bridge location that has to be mitigated rather than 20. And so it makes it faster, and then it's more constructible, and then it's good on the PHPP. Next slide. On the ventilation side, you know, again, we're progressing our design strategy from Cornell Tech, which utilized fully vertical risers for both supply and exhaust. And that strategy took up more floor area in plan, a little bit inefficient. So here on Sendero Verde, you can see it's a little bit more hybrid, and we have one large vertical supply shaft that then horizontally distributes above the corridor to the rooms on the floor. And then exhaust risers are also being shared with multiple apartments. And then, of course, fresh air is being delivered to every room for the renters. Let's go to the next slide. Some ERV, some performance. You know, this is interesting. On Cornell Tech, there were no pH tested ERVs at the scale that we needed. And, you know, we were forced to kind of derate the ventilation in the model and you know, counter with like a lot more insulation in the wall to compensate for that low efficiency number. And so at Sendero Verde, now we are starting to see larger ERVs that are meeting passive house requirements, and it's resulting in a more robust and tested ERV, and allows us to reduce our insulation requirements elsewhere in the project, saving the owner money. You know, and you know, this is kind of like speaking to the buffer buffer that Dylan was talking about earlier, because of the ERV efficiency getting higher, then we're able to, spend the energy budget elsewhere on the job, maybe things which are not as easily solved yet. Next slide. And then here are a few images. This is B South, but like both B North and B South, they're 10 stories. And so, the bulkhead is visible, particularly from, directly adjacent is going to be the Sendero A tower. And so just wanted to point out that, where you're using these PV arrays as screens to help shield view of mechanical equipment, while also generating electricity on the project.
Yeah, so there's a question that came in about how the fresh air is balanced in the building, and really duct sealing is a really important part of that. And one of the things that we've sort of been working through on this specific project is the AeroSeal process. And the thing to keep in mind is that AeroSeal really isn't a widely adopted practice right now. So we were working with the mechanical contractor on this project, who actually very recently got trained on how to do this work. And we were working with them on making sure that they were doing it properly and offering that level of quality control. And there's some specific measures that I want to really highlight, because it's really important when we talk about duct leakage, especially in passive house projects, because duct leakage can be so significant, it can really end up breaking energy models in a lot of cases. If you have 10% more airflow through your ERV than you budgeted for, because it's all getting leaked out and you need to hit minimum airflows in your apartments, that could, if it's not going to jeopardize compliance with passive house certification, it could potentially jeopardize compliance with certain things like incentives. So it's a really critical thing, and we want to make sure that teams are doing this are doing it correctly and to the specifications. One of those things that we found is the photo here on the left is when they do the AeroSeal process. So essentially what they're doing is they're connecting up their fan equipment, which is shown here on the right, to the duct system. And they're pressurizing the ducts to a high pressure and essentially injecting in this aerosolized product that will seal cracks up to 1/2 inch. And it really helps get those sort of nooks and crannies sort of area. And but in order to do that, you actually have to seal off the actual ventilation registers. You don't want air to get out. If you don't seal that off, the test is not going to be, the actual AeroSeal process won't work properly. So what's shown here on the left are the actual foam blocks that go into the duct of the registers that create a nice air seal. And these are sort of spec'd by the AeroSeal company. We've seen some contractors that want to just do their own methods that aren't sufficient. And as a result of that, you get air leakage through those registers, and that causes problems when you're doing the actual AeroSeal process. One of the things that's really critical is as sort of quality control reviewers of the AeroSeal process is reviewing the actual reports. So there's many times where you may see something that looks a little fishy. Now what we're showing here is the red line is essentially the amount of air leakage in the tested duct, the AeroSeal duct. And it's the horizontal axis is the number of minutes that the test is being performed. Now, one thing that you'll see here is that we start off, it's kind of hard to read the numbers, but we're starting off at around 500 CFM. And it drops down almost in half within the span of a minute. That might be something to double check to make sure, hey, are we doing the test right? It's, we expect it to go down, but not that quickly. That's sort of one just general thing to ask. The other thing that you'll see here is at about minute 20, again, it's hard to read, but sort of at the middle of the graph, it sort of spikes up and down and then actually gets higher and then continues to go back down. One of the things that we found on this specific project is that there are multiple settings on the box that hooks up to the duct. Now, if you think about this, if you're familiar with blower door testing, there's rings that you put on a blower door, and there's 3 rings. And if you have ring 2 on and the software is telling you to put on ring 3, the number that you're reading on the screen is going to be incorrect. That's not actually correct. You need to have the right ring on. That's essentially what can happen here. So that's what's causing, these confusing aspects of the result. Why would it get much more leaky and then have to go back down when you've already got it, below 100 CFM? So we're reviewing those reports to look for stuff like that. The other thing we found, there's 2 different specification languages when it comes to AeroSeal. There's fractional leakage, which limits air leakage at 3% maximum. Then the other option is the SMACNA leakage class, which is a different calculation. It's more complicated. Generally, what we see is we see project contractors preferred to go with the SMACNA way, but we've found that the SMACNA path, generally speaking, can lead to more leakage, usually 2 to 3 times more leakage than the fractional leakage method. So we always, next slide, recommend the fractional leakage path. And that's something that we've found to really make sure that we bake into the specs at the start of the project. We also, in this case, actually did our own quality assurance testing of the ducts. So we have this fancy formula here, which is shown here, to convert our sort of low pressure readings to sort of equate to what the high pressure readings of the AeroSeal equipment reads. So that was part of this process.
Yeah, so we called this presentation Narrowing the Gap. And the big reason for that is because we see Sendero as kind of a transitional project from the building codes that we had when we started this project to the building codes that we're going to have when people start moving into this project, which are getting increasingly closer to passive house. So we're both as design teams and as contractors, we're learning a lot and getting ourselves, kind of practiced and prepared for the energy codes of the future. Already those energy codes we're starting to see those changes. I mean, the 2020 energy code changes included requiring documentation of thermal bridges, both linear and point, similar to passive house. There's requirements for testing now. So the air changes are 3 changes versus 0.6. But where they're starting to talk about blower door testing, there are exceptions, but that process is starting to get into energy codes. Balanced ventilation, same thing. There are exceptions in ERVs, but they won't be for long. And then what's coming is there was a local law 32 that was passed in 2018 that requires that the energy code by 2025 set absolute limits on energy consumption of buildings greater than 25,000 square feet. So that's EUI, maybe that'll be carbon emissions. We'll see what form that takes, but that's the big performance threshold that we strive for in passive house, and that's coming to building codes.
So just to conclude here, most of the time us NYPH members were focused on the right side, the private side of this equation, but it's important to realize that if we do our part and, architects and developers were designing energy efficient buildings, that's not enough by itself. To reduce carbon emissions, the governments and agencies must also play their very significant role. We are reliant on the left side of this equation, the public side, to do their part and meet their commitments to transitioning the grid from carbon sources to 100% renewable grids. Both sides need to do this leap forward together to mitigate climate change. And without a cleaner grid, our efforts towards zero carbon electrification are not going to have the intended effect. And us NYPH members, we're ideally suited to advocate for this action. Next slide. And then I know this is a little in the weeds to conclude, but here's our take on New York City's Climate Mobilization Act. Local law 97 is in effect implementing a carbon tax on building emissions over the next few years, phasing in starting at 2024, then 2030. Louis, use your cursor, just show the, yeah. So those are the phasing in points. And then also, New York state government has passed a CLCPA. That's which it's mandating the energy grid being 70% renewable by 2030. So on the left, you see a typical 2018 New York City code compliant EU, 130 EUI building, and on the right is a typical passive house project. And on the left, you can see that assuming business as usual, and then kicking in with 70% renewable energy, you're meeting local law 97 targets, assuming that the grid changes until about 2030, and then you're going to have some high stiff tax penalties. And so the image on the right is interesting because you can see just the one on the left using the current New York energy sources. This is a passive house building. Just by making a passive house, we will meet the emissions targets through 2030, even with a dirty grid. So then when you factor in a 70% renewable grid, by 2035, voila, the passive house building alone is going to allow us to hit those targets. And this is why, at Handel Architects, we see passive house design as one of our main strategies to meet these ever restrictive codes and government mandates. And it's also passive house is one of our best strategies to getting to net zero energy and net zero carbon buildings. Next slide. So And we're going a little bit over today. I want to thank you guys for joining us on this construction check-in. I see there's some questions in the chat, but I think we want to try a little bit something different. We can hang on a little bit longer. Andreas, feel free to jump in if you want, and maybe we can allow the attendees to unmute, and let's just try and make this, be respectful of each other. I'll just start. I have a couple of questions that I'd like to ask, but let's just start. We shared a number of building components and products that started on our passive house projects and have since migrated to our non-passive house projects. And I'm wondering if there are other similar products that you guys have encountered in your jobs. What's great about the passive house community is this knowledge sharing. And I'm just wondering if is there anything that you guys would like to share?
Hey, Ryan and Andreas, it's Sean Torbert out in New Jersey. Great presentation. And then Ryan, thanks for continuing fighting the good fight and tying it all back to climate action. Great stuff there, especially on the last few slides. I was just curious. I'm working on a project where we're looking at several different thermal breaks, mainly for a concrete slab and the footer details. But we were recommended the Fabrica TIM thermal breaks, and I was just curious if you'd seen those. And then one other thing too that we're playing with is this Kingspan Cool Therm phenolic foam insulation, and I was curious if you'd seen anything on how that relates to fire compliance, NFPA 285, etc. If you've seen anything on that yet.
I can speak to the Fabrica. We've used it on other passive house project. It's a good product. I think it's similar to like the Armatherm system. And the Armatherm, I know for specifically with the Armatherm, there's two different styles. There's like an FRR, which has a much higher R value per inch, about R2 or so per inch. And then I think there's the 500 series system. I could get this wrong, but that's a much more structurally superior system, but its R value per inch is about 0.5. And I think the Fabrica is in that realm, the 0.5 R value per inch. The General Plastics, as a comparison point, it ranges depending on what's used, but I've seen it anywhere from R1.5 to R2.5 per inch, depending on the structural class.
Dylan, on that point, there's a question earlier that I think relates to what you were just talking about Armatherm versus the General Plastic block. Like, what are the differences? Do you like thickness, strength, price? Where would you recommend one versus the other?
Yeah, I've had positive experiences with both. I've seen the Armatherm spec more for slab edge details, more horizontally sort of oriented details, as opposed to sort of compression joints and vertical details like roof dunnage and whatnot. We've generally seen General Plastic use more there. In terms of what's cheaper, I don't actually know what is essentially a cheaper product, but like I said, if you can use the Armatherm FRR system, you're going to be maximizing your R value. So I think that's one thing to keep in mind is, do you really need to use that higher superior structural system, or can you get away with their more basic thermal break pad like the FRR, because you're going to get about 4 times more R value per inch.
There are a bunch of questions about the AeroSeal product, and I will, this is something that we're, we started using on passive house projects. We're now using all over on all kinds of multifamily projects, not just here in New York City, but also, throughout the country. So that's one thing. There was a question that came up about that. Is there any concern with AeroSeal particulates contaminating fresh air in the future? And do you have to flush out the system during the commissioning process, Dylan?
So I'm not aware if you need to flush out the system. It might be, it'd be something similar to what you would need to do regardless on the project. There's nothing specific that I'm aware of that you would need to do for AeroSeal. But it is a good question. And the aerosolized product doesn't, pose any sort of fresh air contamination issues. It's something that has been sort of tried and true on many projects, and this has been around. The thing is, it's not like this is a new product that's just coming to market. It's just being applied to more projects now, particularly these multifamily projects where this is critical. But it is sort of similar in process to what's also called the aero barrier process, which is where you actually do this at
Right.
a sort of facade or an interior shell basis where you pressurize an apartment and you get that air seal at the actual walls. And it does something similar. But the actual product itself does not pose any sort of air quality concerns.
So I see in the chat, Sarah Byer mentions that she doesn't have a microphone, but I think this is interesting. She's talking about expanding foam tape. I don't think we've used that, Lewis. Seems interesting. She also mentions it has less GWP. I'm wondering if anyone who does have a microphone who has used this, like, can talk a little bit. Like, is it cost competitive? You know, like, are we, you know, these things are happening on your passive house projects that you're able to use the expanding foam tape on your, you know, quote unquote business as usual, your code compliant buildings too? Anyone?
Are you talking about like an M seal type of like joint expanding foam?
I think she. I'm reading her comment. It's tape, and she was mentioning it in regards to like the non-passive house windows, Dylan, when you're presenting that portion, and how, you know, you're preparing the installation from the inside with a bed of sealant. Like, is there a possibility you could use like an expandable tape or something like that? I mean, maybe it's too new. Maybe it's too new quite yet before we can say whether it's something that can be applicable to all our jobs.
We've considered it on one project. We ended up not using that. We ended up going with a different detail there, but it is something that I think is an option. Windows are tough though. It's you know, material compatibility is a big part.
You can say that like 5 times. Windows are tough.
Windows, yeah, I know. I'm gonna have nightmares. No,
but
it's, yeah.
I was just gonna say on that front, like, you know, we don't use, you know, on a lot of jobs we haven't used UPVC, but that's also like UPVC windows, like the technology, and like we're using Intus windows on Sendero Verde, but like these projects that, you know, passive house, we start using UPVC windows. Now we're looking at them in all kinds of other instances too, and you get a much better U value on the install. I mean, it seems like a no-brainer, but like the technology has really grown leaps and bounds in the last 5-10 years.
Yeah. One of the tricks is how you deal with straps too, from an air sealing perspective. And, you know, on this case, in Sendero Verde, I mean, the builders put a ton of caulk around the straps, and that was, you know, that is our, you know, best way in a way to deal with those tricky sort of areas. You know, we've tested windows that rely on sort of low-rise expanding spray foam as the air seal, and we found little pinhole air leaks, and we found that we actually tested it and it failed on another project. So you know, really, I feel like tape or caulk could work. I've seen caulk be the strategy more so than the tape, I would say, though, and that's partly due to the strap concern.
And Lewis, what about that brick shelf angle detail? Like, we're using Armatherm there, and I'm just wondering, like, I think part of the reason we did that was to you know, it was a detail is very close to what the subs are used to building on a day-to-day on their other jobs, and so it's just a slight, like, trying to just tweak slightly rather than reinventing the wheel. Just do one slight thing, and it's a much more easier to be adapted by the subs. What do you think?
Yeah, I mean, I think that, you know, that was certainly the focus with the shelf angle, and really with all the window install details. I mean, trying to, you know, we had a more complicated detail at those jam conditions that we ended up substituting out for the blocking, because the blocking was something they were doing anyway. It was just a matter of extending the blocking and then using the blocking as the cavity closure. We had a kind of a silicone boot cavity closure in the documents initially. So that's a good example of kind of how we're continuing to learn from the contractors. What are the practices they're using, and then how can we modify those to meet the passive house requirements without introducing, you know, a whole lot of new systems and materials and things that are maybe just adding complexity, but you can get the same or similar result with more conventional practices. The Armatherm shelf angles worked out surprisingly well, and they've, you know, we had some tricky details with them that they struggled with initially, but, you know, getting in the field office there, talking through them with the masons and the CMs, and you just, you know, you get through it, and once they get it once, they you know, it's repeatable around the whole building. So good system.
So one of the things, Dylan, I always find interesting when you talk about using the testing procedure as a teaching tool, as a trying to raise the level of education with the subs and the contractors that we're working with, and then kind of like you're like sprinkling a little fairy dust, the thing gets spread across the entire industry, so like we're like the tip of the snowplow, but like what the subs are learning from these projects are starting to percolate out into the rest of the industry here in New York. And maybe it's a question for the audience, like, are there other testing cases that you've encountered, that you felt really are beneficial and like kind of like help others, whether they're CMs or subs, to like kind of drink the Kool-Aid with us?
I have one little anecdote while we're waiting for others to chime in on this. And this comes from when we do these tests, when we do these, component tests of a window system, like for example, the non-passive house window. And we're doing the test and, we'll ask, is everything airtight before we do the test? Yep, we're good. Window contractor says everything's good, airtight. We do the test. We're 2 times over our air leakage threshold. We have theatrical fog going in it. We're all on the outside looking at the fog where it's coming out. And they're like, okay, yeah, I know why it's leaking. And they'll be able to tell you like instantly, like, oh, it's, well, here's the gasket detail. And it's funny because sometimes you need to mine these answers out of the contractors, and doing the test is sometimes the only way to get them to sort of.
That's so interesting. They probably know who did it. Hey, Bob, you didn't seal this one thing right. Like having these conversations where like then it actually helps inform us and how we describe our details in the future to like try and like bake in some of that. So like getting that firsthand account for how things are working and how the testing is going from the people who actually built it is so beneficial.
Well, I mean, I was surprised that you got more conventional windows to work. And I was actually asked, talking about testing, did you test the assembly like before you actually committed to it in the documents, or did you have to like figure out on site, like incrementally how to actually make it work? Because it seems like a mock-up well before you start construction would have been in order to make that work.
Yeah, so it's either a mock-up before construction starts where we do our air leakage test and we have the window contractor there and we do the same thing, blow theatrical fog in it. If it fails, we don't let the project proceed in terms of if they're constructing, but with windows, but we essentially, we don't approve the detail until it passes the test and we come up with a solution. So sometimes that's in a mock-up, sometimes the project can't afford a mock-up, so we do it on the very first window that gets installed. On this case, I can't remember, Lewis, correct me if I'm wrong, but we tested the first window, or was there a mock-up?
Tested the first window on this
First
job.
window, yeah.
And the conventional windows were only in the areas where we were out of the passive house thermal envelope. So we did have the air sealing to contend with, but we didn't have the thermal components to contend with it. We weren't worried as much about comfort criteria, and those are not triple glaze systems. That's only up where we are within the certification boundary in the residential areas. So those, which in this project are all UPVC.
So what you had described with all of the air sealing and everything like that actually was for not in the passive house area.
That's correct. Yeah,
correct.
It was within the airtight boundary, but not within the thermal boundary.
Okay.
And it is, with the airtight boundary, and Dylan, correct me if I'm wrong, but I mean, this is a very large building. There's a lot of volume. So when you're dealing with that 0.6 air changes per hour, I mean, there is some tolerance for some leakage, which by getting, very airtight up in the upper portion of the building, we were able to, to have that kind of buffer built in for the non-passive house windows in the lower portion of the building.
Oh yeah, I was gonna say, this has been a great conversation between the three of you. I really appreciate it. I'm curious at what stage the phase A or building A, the tall tower, where that's at, and how much what you're going through with these two buildings, south and north, is influencing or impacting that design. at what stage that's at. And I mean, obviously you're doing other projects which are impacting them as well.
Yeah, building A is, as Brian mentioned earlier, it's in closing right now. So the construction should start in July. You can see on screen here, the site right there. So that's where we'll start seeing that guy coming up out of the ground here. Well, I guess I'll go down in the ground first. But we'll be seeing that happen hopefully in July. It's been an interesting process. I mean, building A, we designed and coordinated building A to go first. So that was always the plan. So and then it had to go on hold, and we ended up doing B first, and A got moved to the back. So all the design and coordination decisions on A informed the design and coordination decisions on B, and then all the construction decisions on B are now going to reinform all the construction decisions on A. So we just, we when A went on pause in 2018, we had gotten to about 100% CD. Well, we had gotten to 100% CDs. We were finished with our construction documents, and then we just recently went back and kind of did an addendum set to that, which it captured some program changes and just some things that have changed in the building, but it also captured a lot of detailing changes that we made because of construction issues on B that we were able to now apply back to A. So we're all crossing our fingers that it's just going to be smooth sailing the whole way up.
I'm just saying it may have been a good thing that you started with the smaller structures and picked up some of these things before they ended up embedded on the larger building. Maybe that was fortuitous.
Well, for Passive House Institute's perspective, it's 3 buildings, and the toughest one is the B South. So like we kind of, the one that's finishing first is the one that's most difficult. So like we had to cut our teeth on that one. I would just say that L&M Builders Group is the CM for Building A. So like they're also, it's the same team. So like I think that's pretty fortuitous. And so like the lessons learned, and and L&M's done other Passive House projects too. We know their Beach Green projects. And so there's experience with the developer doing Passive House before. I don't know whether all the people on the current builders team worked on previous Passive House, but like what's great about this is that the same team that was doing construction on B North and B South is now going to shift to Building A, and so like there will be continuity there and reinforcement, and maybe even some of the same subs. I don't know if they've gotten to that point quite yet. There's some questions about geothermal, like, so that one's interesting. Like we're talking about products and things like that we try to use on Passive House jobs that can be used elsewhere. On geothermal, like that's always such a site specific thing. If you can make it work on any project, you kind of want to do it, but like I don't know whether it's anything that's like specific to Passive House, but we have none of our Passive House projects have utilized geothermal. I know Dylan, you've done a few, but I'm just wondering if anybody who and anyone in the audience wants to jump in and talk a little bit about that geothermal. There's some comments in there, so I know some of you guys are more familiar with it than I am.
Geothermal or ground source heat pump?
It's probably geothermal for ground source heat pump.
Yeah, it'd be heat pumps, right? Heat pumps in the units that are sourced from a hydronic loop that is sourced from the ground, a ground loop, basically. That's what we're familiar with on one of the Beach Green projects is using that.
How did you make that work with the pump energy though?
It was tricky for sure. It was also under the FIAS standard. There's a different sort of threshold that we were designing to. The other component to that is that they had photovoltaic energy that they were able to, under that program, use the PV to offset the additional pumping energy. So that was a big part of it.
Have you looked into energy recovery from sewer water? A lot of energy goes out that way.
I'm not as familiar with it, but some folks, some colleagues of mine have studied this. There's been some hurdles to my knowledge. I don't know what those specifically are, unfortunately, but yes, it is something that in theory could work, and it is being looked at. It's somewhat challenging though, but it could work.
A quick question on the sewer energy. Does a high fiber plant-based diet increase that energy, or how does that work?
Yeah, it's a density thing, right? Energy density.
Well, if you think about it, you're bringing water into a building at 55 degrees and then you heat it up and distribute it for use at the tap at around 110 degrees. And that's going back down the sewer pipe and out the building. So you can recover, and there are a number of systems out there. I'll have to look at what I've been looking at. So that's a possibility. It's basically you use a heat pump that uses the sewer water to extract the heat.
That's a cool idea.
Hey, James, if I could jump in here, this is Connor from Intis. We did the triple pane passive house windows for the residential section of the building. I want to backtrack a little bit. I believe it was Dylan, or maybe it was Lewis, who mentioned anchor straps. And this is actually a topic that I've been curious about for some time. And I'm really curious to see, do the metal anchor straps in general, regardless of, you know, if it's an Intis window or whoever's window, does that pose a big thermal bridging challenge as well as an air sealing challenge? I know they really have to be caulked and that caulk is caked on there. But do you ever see through that blower door testing, do you ever see that being a challenge?
So if you break it down into the two components, so thermally speaking, from a heat loss perspective, there's going to be a little bit of thermal bridging as a result of that. One thing that helps is having either thermally broken or a UPV system, because you don't have as much heat entering in from the outside. The other thing to help with that too is really comes down to the detailing of the window termination point at the rough opening. So on Sendero Verde, we were very diligent about, you know, even that extra ½ inch that's overlapping the window jamb really goes a long way. And that's something that we quantify as part of the passive house metric. We can tell you how much more heat flow is a result and how much more heating energy ultimately is what you can extrapolate it out to, is being used as a result of that ½ inch of extra insulation at the window jamb overlapping. And that will help reduce the thermal bridging of the straps. From an air leakage perspective, this one is something that we really learn from doing our intermediate component testing, our guarded blower door testing, and then ultimately the final blower door test is where it would get captured. But like I said, you know, we've found on a lot of projects, just caulking the crap out of them has been a very good solution.
Well, you know, it's really, again, it's something I've wondered for quite some time, because again, regardless of the window, you have all these metal straps that basically extend to the outside of the window right into the building. Then you have puncture points along the jambs with screws. And I'm curious if avoiding that and maybe going to like an interior snap trim, which would be like an L angle or a 90-degree angle that's affixed to the inside face of the window, if that would eliminate some of those issues. Now, if it wasn't a big issue, then maybe it's a moot point, but it sounds like that could be another area to eliminate some thermal bridging and make the whole air sealing around the window much simpler if you don't have straps extending all the way to the side of the window. Yeah.
I believe at one point we were tossing around a detail like that for building A that showed the angle there on the inside. So I've seen a similar strategy. I think that could potentially work.
Oh, don't get any ideas, Dylan. That the addendum 1 is now done.
The 2 is now done.
Blame Connor, not me.
Sorry, folks.
So I think a challenge with that is also just the install detail with you know, because if the angle is attached to the inside of the frame, you need a thicker frame, you know, so then aesthetically you don't want to see that thicker frame on the outside, so you're trying to cover up more of the window with the exterior cladding potentially. So I think we did kind of sketch around some ideas around that, and it made the install detail quite a bit of a challenge. I mean, it helped with the thermal bridging, but it was difficult to figure out where to put the wall, where to put the window within the wall. Kind of the relationship of everything was a little bit unconventional.
All right, great. So like I know Dylan, you have a going away party for a colleague of many years. So thank you very much for being able to stick on an extra 20-25 minutes here. This is a great discussion. I'm looking forward to the day when we can all get together again and have these informal conversations. Maybe a Passive House conference. I don't know. Is it going to be live this year? I don't know. What are you NYPH folks can chime in here, but just wanted to say, oh, great, Andreas. So thanks for having us, and if you have any concluding comments.
Yeah, I would like to thank you guys for presenting. It's a fantastic presentation, very detailed and very helpful for, I think, for everyone to get into the multifamily passive house world. I think, like Koehl reminds us, the zero energy or zero emission laws are coming, and they're coming for small and large buildings. So it's great that you are preparing the industry for that point. I think the transition is easier once we have very good examples out there. So thanks everyone for doing the work.
Thanks, Andreas. I would say that we are preparing the industry. NYPH, you're some of the loudest. We're not a huge group, but we're some of the loudest ones out there.
Yeah, I mean, it's great for any practitioner who is participating, and it's great to add that knowledge to the overall knowledge things for everyone. So thanks everyone for listening. Thanks for presenting. Was great.
Thanks for having us. Thanks. Bye-bye.
Thanks everyone.
Thank you.